Welcome PCS members and friends to our today's IBS PCS Tuesday seminar. Today it is a great pleasure to have with us Professor Giuliano Benenti from University of Insubria. PCS members and friends to our today's IBS PCS Tuesday seminar. Today it is a great pleasure to have with us Professor Giuliano. Yes, I apologize for the echo. To continue, I would like to invite our scientific host, Sergey, to introduce our speaker. Please, Sergey.
Yeah, thank you, Tilen, and thanks, Giuliano, for joining us and preparing for a second talk this year. Giuliano Benenti is a frequent speaker in our series of talks and gave already a talk very early this year. And maybe we will even meet each other in person later this year. But for now, I also want to mention that to everyone that we are slowly shifting into hybrid mode. And maybe some of you can see that there's a big and empty seminar room with our convener Tilen sitting there and pushing all the buttons. So this is our new era, which is now starting. And I hope it will all go well. And apologies to everyone if there is any glitch coming up during this presentation. So let me say a few still words about Giuliano, especially for those who haven't been here during his previous talk. Giuliano studied physics at the university in Pavia, and then he did his PhD at the university in Milano on quantum localization in Rydberg atoms. And then he had, this was in 1998, and then he moved to postdocs in France and also in Italy, and then settled down, so one could say, at the I don't know how to pronounce it correctly, the Università degli Studi dell'Insubria, which is somewhere close to Como, because it says Sede di Como in Italy, where he moved up the ranks and is since 2015 an associate professor. He is known for a lot of excellent research work in such fields as thermoelectric transport, heat transport, and thermal rectifiers. In general, far from equilibrium quantum systems, quantum computation and quantum information, many-body quantum systems, disordered systems, and nonlinear complex systems. And I hear some strange noise. I'm not sure where this noise is coming from. Everyone who's not involved, mute yourself. Right, and Giuliano has a lot of publications which you can find on Google Scholar. And one of the reasons why why we asked Giuliano to present to give this presentation today is this reference, which I think we see in the bottom part of the slide, the first slide, the other reason is that Giuliano worked for many years together with Giulio Casati, who's also located at the same university in Como. And they recently produced this interesting paper on classical physics and blackbody radiation, which sounds very intriguing. And that's why we asked Giuliano to give us a talk on that and tell us what we should learn about classical physics and blackbody radiation. And with that, I should stop blathering around. Giuliano, the floor is all yours. Please go ahead.
Thank you very much, Sergei, for the invitation and very nice introduction, too kind. And well, it's of course a pleasure giving a seminar, and hope to see you face to face quite soon. And now, well, I should thank also my collaborators in this work, Zhao Wang from University of Xiamen and Giulio Casati here in Como. And then, well, you see from the title, it's a very, very old problem, blackbody radiation. So everybody learned about this problem during quantum mechanical courses. And so, sorry, okay, it works, sorry. And then the question is, why should we go back to such an old problem? And there are reasons. One reason is, if you want, from the viewpoint of dynamical systems theory, because this is, the problem of the ultraviolet catastrophe was based on equipartition theorem, but now we have a system with a field, the electromagnetic field, so we have an infinite number of degrees of freedom. So it's not even clear what is ergodicity in such a context. So this is, if you want, one motivation is from theory of dynamical systems. And then if you want, there is a more general curiosity, I mean, again related to dynamical systems, but say, assume that we take Maxwell-Newton equation. We try to find a system that is solvable numerically, treatable. And we solve the equations of motion, and then we will have equipartition or not. We will have ultraviolet catastrophe or not. And I can anticipate main conclusions, and then I will elaborate, of course, that actually this is not the case. We achieve a kind of, not a steady state, but a quasi-stationary state, which is compatible with classical thermodynamics, with the Stefan Boltzmann Law. And there is a frequency cutoff. So it seems that ultraviolet catastrophe is not an avoidable consequence of classical physics. And of course, I do not want to repeat old history, but this is very, very famous problem, very important for the beginning of quantum mechanics. And I took this page from Feynman's lecture on physics, first volume, chapter 41, and you see there is this picture with intensity of the blackbody radiation versus frequency, and you have the Rayleigh-Jeans law with the ultraviolet catastrophe at different temperatures, and then you have, Planck's law, and you have high frequency cutoff. And but it's interesting because if you look at this, what is written there, there is this count of frequencies per unit frequency range, equipartition, and so on. And they say, okay, if you use equipartition, we know it is false because if we look at high temperature radiation, we do not burn our eyes from X-rays and so on. No? And then, this is the interesting point. Classical theory is absolutely incapable of correctly describing the distribution of light from a wave body, just as it was incapable of correctly describing the specific heats of gases, of course, at low temperatures. No? Physicists went back and forth over this derivation from many different points of view, and there is no escape. That is the prediction of classical physics. So this is the equation he refers to, with the intensity proportional to temperature and frequency square. It's called Rayleigh's law, and it is prediction of classical physics, which is obviously absurd. So, in Feynman wrote that is an unavoidable consequence of classical physics. And if you want, it's quite strange that there was such a sharp statement on something which is based on equipartition principle. I mean, but ergodicity was never, apparently was not, this was taken for granted. And ergodicity was not thought that the problem was about ergodicity. This is another viewpoint that this is from Max Jammer, another famous book on conceptual development of quantum mechanics. And this is also interesting because he says that it's unfortunate, it was unfortunate that first problem dealt with in the development of quantum theory was the blackbody radiation problem. And the point he raises that it was in a sense a too complicated problem. So it was understood in terms of, quantization of energy exchanges, and there was no quantization of matter. And so he said that probably starting from another problem, from a specific heat of gases, the development of quantum mechanics would have been faster. That's another interesting viewpoint. Of course, this is a Planck's formula. And then another point that, of course, everybody knows is that the Planck's distribution is ubiquitous. So I just show, this is from the website of University of Hannover, and they've chosen to celebrate Planck's discovery, a candle, as an example of blackbody radiation. And this is, very famous image, cosmic microwave background radiation. And you have COBE data, and that are very, very nicely fitted by Planck distribution. So, well, of course, it's an important problem, a very ubiquitous interaction between radiation and matter. And as a motivation for our studies, of course, no comparison at all for what they got, of course. But as an inspiration is this famous Fermi-Pastaula-Matsingu model, and where they integrated numerically equation of motion for a nonlinear chain. And the question was about equipartition of energy between harmonic normal modes. And I took, this is a very nice reading if you are interested, a FIS report long ago by Joe Ford, and these are original data from Fermi-Pastaula-Matsingu, and energy, you see there is, as a function of time, there is no equipartition of modes, of energy between the modes. And of course, an entire field started of nonlinear dynamics from this study. Of course, there were questions. The number of modes was enough or not enough, the integration time, and how the threshold for ergodicity evolves with the number of modes, and so on. And you know why we were taking this as a source of inspiration, because of course Fermi and co-workers knew very well that specific heat of gases was this was a problem well explained by quantum mechanics. But nevertheless, they were curious to know what would have been the outcome of classical mechanics integrating equations of motion. And they put a nonlinearity, this cubic nonlinearity, and they found some, at the time, I think, very surprising result, that there was this lack of equipartition. So taking this as general motivation, so there is some more recent, but not so recent, because we go back to 50 years ago, but similar in spirit idea. And this is some model we have generalized in our study. So these people, Bocchieri, Crotti, and Loinger, they try to do something similar to Fermi-Pastaula and try to solve numerically the Newton-Maxwell equations of motion. And so the question was, could we find a model simple enough to be treated numerically? And so they consider, first of all, they try to reduce dimensionality to have a one-dimensional model. And so they consider a plate, a infinite charge plate, which can move only in vertical direction, so in the z direction, is in between perfectly reflecting mirrors, is in the middle between these mirrors. And so you can write equation of motion. You have potential vector, you choose a gauge, and you have delta distribution for the charge of the plate in the transverse direction, and then you have sigma, which is the intensity of your charge per unit area. And so if you solve the model like that, it is linear, it is solvable. You can find normal modes, overall normal modes for the cavity plus the field. And of course it is linear, and being linear, there is no equipartition at all. So the question is, what about if nonlinearity is added to the matter, to matter? And so the authors added a restoring force for the charge plate, like a cubic restoring force, like the cubic force in Fermi-Pascaud model. And then they started some numerical investigation. This was long ago. There were papers following by Giulio, Italo, Guarneri, and Vasgris, other people like Levi, Vulpiani, and so on. And quite curiously, it was okay, there is a question, maybe. No?
Okay, I would like to specify the system of this cavity. So, so what is the dipole which is emitting the radiation, if I correctly understand the system? Or there is some dipole, because normally if we want something to emit light, this is the dipole. Is this the plane or it's not?
No, the plate is uniformly charged, and we assume that this plate can move vertically. Okay, and then you have reflecting mirrors and the field inside the cavity. This is your black body. So you write for potential, for potential and scalar vector the equation. You have the charge, which is delta distributed, and then you have the current, because this plate can move. So you have this z dot. Okay, so you have the plate which can move. So depending on the velocity of the plate, you have a current. Okay.
Okay, so we have a current, so some acceleration of charge, and it produces the radiation. And so I have also question. So if this system is it is confined between mirrors, so from the outside we see nothing. We just have the observation which is done from inside this system.
Yeah. It's an ideal situation, infinite mirrors. Yes. This is ideal case. Absolutely. Yeah.
So in some sense, there is transfer of energy between the modes of these resonators, resonator between the mirrors and the photons which are produced by the motion of this charge plane.
Exactly. So the question is, assume that you give initially your energy to the plate, I don't know, some velocity. So then you have interaction with the modes of the field, and the question is if you populate the modes of the field to higher and higher energies. That's the question. Okay. If you achieve some kind of equilibrium between the plate and the modes of the field. Okay.
Okay, thank you for the description of the system. Now I understand it much better. Okay, thank you.
Thank you for asking. Then the question is if with nonlinearity you can have a kind of thermalization. That's the point. And populate the modes of the field and define a temperature and so on.
Excuse me, Giuliano, just as a follow-up to the previous question. So if you take this plate and you give it an initial velocity, it starts moving. What will happen then? We're still in this in the framework of these linear equations, as you call them. So will it start oscillating, or what will the plate do, or will it move on forever, or?
If you have, if you are in the linear framework, then you will have a mode with, you have also, you have also a zero frequency mode. So you have also a mode that moves forever. Yeah.
You mean that the plate will move forever?
I think so. I should check this whole derivation, but I think so.
I mean, Z dot is an conserved quantity. Then is that what you say? Z dot is the velocity of the plate, right? Yeah.
Let me think about. I have to check because you have I mean you have like infinite matrix that you can diagonalize, and then you find the roots numerically, basically, of a field plus plate.
If I may ask you, okay, well, maybe we can discuss it also later, but if I may ask you, why choosing this set of this problem as opposed to the Fermi-Pastor-Ulam-Zingo case, which has a finite number of degrees of freedom and things are much simpler? Is that you wanted to have a model which has an infinite amount of degrees?
Yeah. That's exactly the purpose.
That was the point, I see.
I want a model with infinite degrees of freedom and the spectrum which is not upper bounded. That's the
you could technically do the same with the Fermi-Pastor-Ulam-Zingo case, just take an infinitely large lattice, so to say, right?
No, but if you take infinitely, I mean, you take the thermodynamic limit, that's what
yes.
Yeah, but then you have a band, no? I think for
and here? And here not, I see.
Here, no, it's unbounded, the spectrum.
I see. So you have an unbounded spectrum. That's the point, I see.
I want to treat a field, that's the point.
Okay, thank you.
Okay, welcome. And so the question is, what happens if you add a nonlinear restoring force to this plate? And there were studies in the 70s, 80s, and also I had a paper when I was a PhD student. But basically, the point was that it was not possible to see a clear tendency to equipartition. I mean, maybe the model in this model, the nonlinearity in a sense was weak. Maybe the computers we had at disposal those times were not good enough. So it was, we wanted after so many years to rethink about this problem. And okay, maybe there is
sorry, I have another question. So what is then, back to this linear problem here, what is the spectrum of these modes? Is it continuous? Is it discrete?
No, it is discrete. You have the frequency of the cavity, which goes linearly with the wave number. No, so omega k goes like a k, say, no, and then when you add the plate, you have frequencies which are in between frequencies of the unperturbed of the cavity itself. Okay, so you shift the frequencies basically, and the shift becomes less and less when you increase frequency.
Okay, but again, so is the spectrum of these linear modes, is it equidistant?
Yes. Yes, it's one-dimensional problem. That's the point.
Yeah, but you say equidistant. That's what you say.
Yeah.
You could have you could ask what happens if you take instead a non-equidistant spectrum.
Yeah, that's a question. So one of the things we would like to investigate in future is going beyond the one-dimensional model. So you have something which is different, and how the conclusion will change in that case. That's yeah.
Okay, thanks.
Okay, welcome. And so we modify the model. You can see it's a little bit awkward, but well, this is a schematic drawing. We add other neutral plates, so we have just one charge plate, which is connected to neutral plates, and we put nonlinearity in these plates. And the idea is that the motion of the charge plates, the system is complex enough that the motion of the charge plate becomes essentially random. That's the point. And then the charge plate interacts as previously with the cavity. So the idea was to make a stronger randomness, to see if we can populate higher frequency in the field. That was basically the idea. So this is the topology of the model. We have the charge plate, this one, which interacts with neutral plates, with plate 2 interacts with 3 and 1, and so on, and we had a given number of plates. We take 16 plates in our simulation, and we saw that it was more than enough. There was no need for our simulation to increase the number of plates. It wouldn't change the results. And then we have, in principle, infinite modes for the field. And of course, you have to cut off these modes for numerical simulations. And then you have to understand what is the impact of this cutoff. That's the point. Okay. So in more details, we have Hamiltonian. So the first part is for the plates. So you have harmonic interaction V of Zj minus 1 Zj between the plates. And then you have quartic restoring forces for the plates. So this is the 5-4 model. And we check that if you look just at matter, I mean just at the plates, for a number of plates larger than 4, the model for the energy we were considering in our simulation for the total energy, the model was chaotic, I mean with NP positive Lyapunov exponents. I mean the size of stability island was negligible for numerical simulation.
Question, why 4?
Well, because for the energy, of course, is a transition of the KAM type. No? So you will have a threshold, and the threshold will depend on energy. So for the energies we use for NP greater than 4, we didn't see any island. That's the point.
What I mean is, why not 3? I mean, normally 3 would be enough.
Okay, maybe. Okay, maybe that's okay. This I should check again. I should check again the data. It depends on the energy you use, also. I think, no. But okay. Anyway, we use much larger. We use a 16 to be sure that up to the time scale we integrated, and the energy we consider the system was chaotic. That's the point. And then you have coupling. Z1 is coordinate of the charge plate. P1 is conjugated momentum. So you have coupling with the field. This is the coupling term. This is velocity. Okay, velocity square. Epsilon is some rescaling of the charge. Sigma is the charge per unit area. L is the separation between mirrors. And then you have the modes of the field with coordinates QK and PK. And you have at frequency omega k. and you see the frequency, c speed of light, and frequency goes like k. And only even, okay, you have even and odd modes, and only one kind interact with the plate, because the other modes are for symmetry reason, because you put the plate in between, in the middle of between the mirrors. They do not interact. This is the reason of this 2k rather than k, but okay. This is just a detail. And then we put a normalized transverse charge distribution. We did not limit to the delta distribution. And the reason was that we wanted to be sure that the results were not affected by the kind of charge distribution you use. And so is it clear, the model? Do you have questions about this model? So you see there are matter interaction between the charge plate and the modes of the field, basically. And you see this coefficient AK is where the charge distribution appears, because these are the Fourier coefficient of the charge distribution, the transverse charge distribution, the transverse direction connecting the mirrors. So if you take delta distribution, okay, maybe I can, okay, I didn't put here, okay. Sorry, if you put delta distribution, this AK doesn't depend on K. We use a different distribution for which AK drops very fast, and we check that we got qualitatively the same results. That's the point. And maybe I will be back on this detail. But so you see, the model is quite artificial, but still it captures some essential features, the essential features of field-matter interaction. So the field modes exchange energy not directly, but mediated by matter. And the electromagnetic field in the cavity is linear. Nonlinearity is provided by matter. And frequencies for the field are not upper bounded. They're basically ingredients. And then we check, first of all, relaxation times. So assume that you consider now finite number of modes for the field, and you integrate very long, ideally infinite time. You will have equipartition. That's not the problem we want to study, because we want the opposite limit. Integrate up to a given time, but infinite frequencies for the field. But let us check now equipartition times. So we take n number of modes for the field, and we integrate very long in time until we reach equipartition. We use some equipartition indicator, so a kind of entropy, energy that goes to each mode of the plate or of the field. So this kind of entropy, then you take exponential minus entropy, and this quantity is 0, is 1 if you just populate one mode, and it is number of modes if you have equipartition. And so you average over time, up to a given time. And we check the time to reach, say, 90% of equipartition value. And you see that we take a given number of fields for the plate, and changing the number of fields in the modes, the number of modes in the field, you see that the equipartition time for the plates is almost stable, but the equipartition time for the field increases exponentially with the number of modes. So,
Giuliano, again, so relaxation time is defined how?
Yeah, you see, we compute the energy that goes to plates and to each plate and to each mode of the field. Okay, you average over time, and then you compute this kind of entropy, which is energy times logarithm of energy, time average, and you sum either over the modes of the field or the plates. Okay, this quantity is 1 if you just populate one mode, and is a logarithm of number of modes. Well, no, is 1 over number of modes.
Okay, I got it. But my question, I guess, then is, what is your initial condition or your initial state?
The initial state. Well, we gave energy initially to the plates.
Only
Only to the plates.
How?
You can also give energy to some mode of the field, but it doesn't change.
To all the plates randomly, or only to a few of them, or how? What did you do with the plates?
We did randomly, typically.
Randomly, but only to the plates. So okay, and
yeah.
And then you want to know. So this is okay. This is so your cavity is unpopulated, and you want to see how long does it take for the cavity.
Yeah. But I want to stress that assume that you populate, say, one mode of the field. It will not change qualitatively this
again field. if you excite also one mode of the field, nothing drastic different will happen.
No,
I understand, but essentially your cavity is empty, and you want to see when does the cavity is filling up, so to say, right?
Yes. It will not change essentially because you see everything has to go to the plate, so if you populate one mode, then it has to go to the plate to populate the others.
Okay, thank you.
So it will not change much. And then we took this charge distribution for these simulations. So this is a infinite compact C infinite function. Delta is the width of your plate. So you can derivate, you can derivate infinite number of times, but it's non-analytical because the charge is 0 outside the plate. This means that the Fourier coefficients drop faster than algebraically. And then we compare with other limiting case, which is the delta distribution, where Fourier coefficients do not decay at all. And we got practically the same result, qualitatively the same results. So this was a test of robustness for our model. Okay, now I come to our results. So first of all, the appearance of a quasi-steady state, because, okay, J are the plates, and omega k are frequencies for the field. And then we plot average over time of the energies at different times, from 10 to the power 5 to 10 to the power 8. And you see that you have equipartition up to some frequency, and then you have an exponential drop. And if you go to 10 to the power 5, 6, 7, and 8, you see that slowly you start populating more modes of the field. And we took in this simulation 120 modes of the field, and we checked that, well, there was no reason to increase further because results were absolutely stable. These are quite a delicate simulation because we had to take a very small step for Runge-Kut integration step, because otherwise at very long time you start populating artificially some modes at high frequency if you do not take a small enough integration step. So overall, I mean, it was a huge effort numerically. It took several months of computation time. That's the point. And it's possible. It wasn't possible 20 years ago. That's also one of the reasons to re-examine this problem. And so this distribution evolves logarithmically in time. You see just already from this plot, very slowly. And so there is no ultraviolet catastrophe in this model. That's, if you want, the first conclusion. Then you can try a scaling, and you can scale for a given energy different times, or for a given time, different total energies of your model. And the scaling, you have scaling parameters which depend on total energy. And basically what you have is that if you increase total energy, you need smaller time to populate higher modes, higher frequencies. But this doesn't change the exponential. The exponential is low population and the exponential tail. That's the point. Then why this result? Well, it's curious because you could say it's exponential because you see here the field modes decay very fast, faster than algebraically. But the point, okay, I didn't show here data, but we had the same exponential decay also for the data distribution, where these Fourier coefficients do not decay at all. We put in our paper in the supplemental material. So it's not the charge distribution that determines this exponential scale. So of course we do not have, unfortunately say, we do not have any analytical result. We can provide a qualitative argument that if you look at the power spectrum of the charge plate, you have some frequency band in a sense, and then you have exponential decay. So the idea is that your plate couples very well with modes which are inside this frequency. But then the coupling to modes outside this frequency is exponentially slow because the power spectrum decays exponentially. This was the main idea. And you see that if you increase total energy, then the frequency band for the power spectrum increases. And indeed, in that case, you populate faster the modes. And indeed, you have this scaling. But again, you have then an exponential decay. So qualitatively, you do not change your conclusions. Okay, so that's the point. Okay, maybe if I have other minutes, sorry, it was a little bit slow. Now you have a quasi-steady state. So, and you have a plateau where you have thermalization. You can define a temperature. And then the point is it possible to build a thermodynamics for this model? And it's not equilibrium thermodynamics, but it's quasi-equilibrium. So what are predictions from classical thermodynamics? Well, we have a Stefan Boltzmann Law, which we know is in agreement with experiments. The energy, the density of energy for the black body goes like T to the power 4. But this is for three-dimensional case. We are in one dimension, so we can rederive the Stefan Boltzmann Law. So we start from a fundamental thermodynamic relation connecting energy, entropy, and volume. Then P is pressure, and T is temperature. Then you derive over volume at fixed temperature. And then we use Maxwell's relation. So rather than entropy, we can use pressure, the derivative of pressure over temperature, given volume. And then if we assume equilibrium between matter and radiation field, we can derive that in one dimension, the energy per unit volume is equal to the pressure. In three dimensions, you have energy over free, and this gives you the Stefan Boltzmann Law in three dimensions. So we integrate the equation above, and we get the Stefan Boltzmann Law in one dimension, that the density of energy goes like to the temperature to the power 2, which is in contradiction, by the way, with the Rayleigh-Jeans law, where according to which the energy goes like temperature. And this, if you want, it's quite curious that in all the times, I mean, it was taken for granted that the contradiction was in classical physics due to the Rayleigh-Jeans law, but it was in agreement with thermodynamics. I mean, there was no contradiction with Stefan Boltzmann law, which you can derive also in classical physics. But it was taken for granted, the equipartition theorem. That's the point. And so how can we compute these thermodynamic quantities? Well, the temperature of matter, you can take the temperature of the plates, you can take the energy of the plates, you take the mean over time, and then you have temperatures. Okay, you can take the plates or the thermalized modes, and you get the same temperature, of course. Then the density, the density of energy in the field you can measure. And because you have the energy of each mode, and you sum up. And then to compute the pressure, we perturb the distance between the mirrors. We change slightly the distance. And we look how this changes the energy. And out of that, you derive the pressure. So you have pressure and temperature, which are in good agreement, as you expect at equilibrium. Then, pressure and density of energy. Then you have temperature. And so you can build a plot with density of energy in the field versus temperature at different times and for different values of the total energy. And you see that you have a power law with a slope which is larger than 1 and increases slowly, very slowly with time. And you would like to get 2 for Stefan Boltzmann, while ultraviolet catastrophe Rayleigh-Jeans gives power 1. And but is T to some power, but power depends on time. And if you fit the distance from Stefan Boltzmann, you have this inset. And so this is compatible for the fact that eventually, we don't know, of course, but eventually you might reach the Stefan Boltzmann, so agreement with prediction from thermodynamics. That's the point. Okay, so I think I'm running out of time. So what is, the outlook of this model? Well, first of all, there is a result that you have some thermalization, which is fast for the field modes, which is fast within bandwidth for mechanical mode, and it is slow outside. So if this is the mechanism, we can conjecture that this will be a generic feature of field-matter interaction and not just of this very specific model. Then, of course, there are questions that it would be nice to extend to higher dimensionality, to check if there is, in this case, thermodynamic consistency, the Stefan Boltzmann law. Then in this case, the energy goes like T to the power 4, so it's clearly much clearer distinction with equipartition. We have also Wien's displacement law of the maximum of the Planck's distribution, and this could be hopefully checked. And then, of course, there is question about quantum case, if one could be able to study some quantum model with similar feature, what would be with a field interacting with matter. In the case of field, infinite dimensional system of this kind, what would be the quantum case, the lack of ergodicity? This is, I think, some interesting question. Okay, so thank you for your attention and for comments and questions. Thank you very much.
Okay, thank you, Giuliano. And I'm not sure whether Tilen is
yes,
there.
I'm here Yes, thank you, Professor Benenti, for this interesting talk. Let us thank our speaker.
Thank you.
And we are open for questions.
So maybe I should, let me start with just getting some, understanding some more things. So, so this was intended to show that if you have, under certain conditions, let me phrase it mildly, under certain conditions, if you have a cavity with an infinite set of modes and an unbounded spectrum, if you couple that cavity to some other system which has a finite bandwidth, so to say, then even though that subsystem is maybe thermalizing, it will take forever to thermalize the cavity. Is that what you are telling here?
Yeah.
Right? And then this time increases somehow in some way with the number of modes in the cavity.
Yes.
And what is that now telling us in terms of, so what has that to do with the blackbody radiation and the entire discussion which happened 100 years ago, so to say?
Yeah, well, I would say, of course, the purpose is not if we get Planck's distribution or not, of course. Well, you get an exponential cutoff, not like in Planck distribution, but the question, the main question is not if classical physics.
Let me interrupt immediately. You get an exponential cutoff in what? I mean, I thought I saw that you have an exponential dependence of the thermalization time on the number of cavity modes.
Yeah, but the point is that after the plateau, you have exponential cutoff. And it takes very long to move this distribution. You know? So if you take 50 modes and I don't know, distance between mirrors 1 meter and you play with numbers, it takes you more than the age of the universe to thermalize 50 modes. So for all purposes, it's like having a stationary distribution.
Yes, but it's still changing in time, right?
Yeah, it changes in time. That's important.
But very slowly, you see.
But very slowly. Actually, this was some at the beginning in the historical. In the history of the black body, there was also some conjecture like that by Gibbs, but it was later rejected, apparently. But I mean, the point is not if you reproduce data or not, but the point is if the ultraviolet catastrophe, which is at the, at the beginning of quantum theory, is really an unavoidable consequence of classical mechanics or not. Because if you think it's quite funny, also this, what you have here in Feynman's lectures, it's quite funny because he says that is an unavoidable prediction of classical physics. So people at the time knew very well that prediction of thermodynamics, Stefan Boltzmann Law, were in agreement with experiments, and this doesn't require quantum mechanics. And they knew about, equipartition principle, and they took it for granted. Apparently, it's quite funny that it was not questioned the validity of the equipartition principle, but the conclusion was that the classical physics was wrong. That's the point which quite straight.
In some sense, it is not the equipartition principle is not I would say is not violated also in your studies. It just takes forever. So what you try to say is that it takes forever to observe it because of this.
It takes forever, but you understand that if you take 1 order of magnitude to populate a further mode of the field, it's like being at a steady state, no? So
the reason for that is, of course, the fact that you have that the injection of the energy comes from a certain finite band, energy band, and the cavity modes you are studying are out of resonance with it, so to say.
Yeah, unavoidable, they become out of resonance, yes.
Right. What can you say about this exponent there, which you observed?
This exponent, this
yeah,
there was this of course we do not
not this one, the other one. If you can show please again the energy distribution.
Sorry, maybe it's later.
Yes, this one. So there is some exponential decay, right, on the right part of the plot.
Yeah, yeah.
And this exponent, this decay, what is it?
You mean in terms of temperature? Well, all that I can say is that we can rescale these curves, but well.
Yes, but my question is, how is that exponent related to the bandwidth of the plate system, so to say, and well, to something else maybe? It looks like some classical version of Planck's constant, which you have here. So what is this? What is this? Where is this number coming from? That's in a scale, right? Which one could derive maybe.
Okay, we didn't try. Maybe one could derive like that. In a sense, this slope depends on total energy. So in a sense, it depends on temperature, and then with this scaling, you put this curves one over the others. To derive classical version of Planck constant, but we didn't try. One could try for fun, but again, this was not the purpose. It was not that we want to predict from classical mechanics the blackbody radiation, but was if classical mechanics predicts ultraviolet catastrophe or not. That's or if you want, what is ergodicity in these in fields, in these infinite dimensional systems. That's
okay, thanks. Maybe I should stop here, and I don't see raised hands. Maybe some others have questions. Seems not to be the case. Then let me continue. PCS2 tried to say something. That's Tilan, I guess.
No, please go ahead, Sergey.
Yeah, so in some sense, boiling this down to maybe, well, maybe disentangle this from the general issue of blackbody radiation, and coming more to focusing more on the question of equipartition and thermalization and the such. So what you do here is you look, in some sense, you look at some heterogeneous system. Yeah, you have one part which is your plates. The plates, you construct the plate system in such a way that this Hamiltonian thermalizes reasonable in a finite time. So to say, no matter how long you have to wait, in some sense, no matter how large your system is, doesn't depend on the number of degrees of freedom in that plate system.
Yeah.
And then you couple that entire system to some other system, and then you use the fact that you have non-resonant modes, an infinite set of non-resonant modes, right? Mm-hmm.
Yeah.
So what would be some example from real life physics where we can run into such a situation?
That's yeah. Yeah, that's a difficult question. It would be nice to have, I don't know, ideally, I don't know, two interacting charged particles in some enclosure. I don't know. With interaction, you would have nonlinearity and small set of interacting particles, I mean, in some enclosure. And what do you get? But then the point is that then mirrors are never perfectly reflecting, and yeah, I don't know, to have such a situation. No, maybe one could think about some field. Okay. Yeah, no, I mean, field, how to say, matter field interaction, of course, is generic, but now if you want a situation where you can experimentally observe something like that, well, I don't know really. That's okay, I cannot, because one should be able to isolate and then observe also. Should be some escape which does not perturb the rest, but you can observe somewhere. Okay, please, okay, sorry, but I cannot tell more.
Okay, there's a question by Mirab.
Please.
Hello, and thank you for the talk. I had actually two questions regarding your model. Maybe I missed it, but could you please repeat what is the importance of not a bounded spectrum as opposed to Fermi-Pasta-Ulam model in what you consider? So this is question number one. And also the question number two is like this. So in FPU, the initial conditions are highly atypical. Could you please comment in your case on the atypicality of or typicality of initial conditions?
Yeah, well, about the spectrum, the point is that I mean, if matter has a bandwidth and then you have unbounded the spectrum, eventually you go out of resonance. So the question is, when you go out of resonance, do you still have a tendency to populate this mode and go to equipartition? And if so, how much time you need or not? Mm-hmm. Or you just at some time you stop populating mode. That could be another option. So it's, in a sense, it's different situation from Fermi-Pasta-Ulam. That's the point. No? Then you said about initial conditions. Okay, I would say that for the overall picture, initial conditions actually do not matter, because the point is, assume you give energy just to the charge plate. Then matter is very nonlinear system, and so you populate quite rapidly the parade. So how you choose your initial condition for the plate doesn't matter very much. Then you have the question about modes. So typically we started with energy given to the matter. That's okay. But we also did some simulation. We start with energy to just one mode of the field. Then what is the point? That this mode of the field populate the charge plate, and then you start again with the same game. Because interaction has to be mediated by matter. So eventually initial conditions are not relevant in the long term. Of course, you have a transient which can be also very long when if you populate the field, then it can change, but eventually you will have the same behavior. That's the point.
Mm-hmm. Then I have the following question. Could one also alternatively start from some thermal initial conditions and then study some thermalization times and so on? So does one need to study to start from non-thermal initial conditions, as you do, as far as I understood?
No, well, not necessarily. Well, we studied the problem is we studied a closed system with a given total energy. That's our problem. I mean, in principle, one could also start from a thermal initial condition and study the evolution, but the purpose was closed system with total energy. Given total energy, can we define temperature, thermalization, and so on? That's,
Okay. Thank you very much for your talk.
Okay, other questions? Maybe Giuliano, just want to add. I think what Mirab had in mind is that what you can do is you take, your system as it is with a finite number of everything, including also finite number of cavity modes, and then you thermalize it. You are excited, so to say, in a random way, and then you let's say compute some Lyapunov spectra. And then you look at the properties, you try maybe to say something about the properties of these Lyapunov spectra as you increase the number of cavity modes. And then probably something funny must happen in these Lyapunov spectra, because a lot of Lyapunov exponents will probably start to gather very close to zero, because these modes are basically very weakly coupled somehow because they correspond to modes which are weakly coupled to the strong chaos which can happen inside your plate system.
yeah, that's a nice suggestion. Yes.
Maybe, I don't know, yeah.
Yeah, this can be worth studying. Yes. Okay, thank you.
Okay, other questions? Seems not to be the case, then perhaps I can give things back to Tilen. Tilen, please take over and conclude.
Yes, since there is no further questions, let us thank Professor Benenti again for his excellent presentation.
Thank you very much for inviting me. Thank you for questions. It was stimulating for me. Thank you very much.
Yes, and hopefully soon we meet you here in person also.
Hope so. Really hope so.
And with this, we conclude our today's